we discussed on those last two sessions, we discussed about the precision agriculture introduction and component, uh, soil properties, electrical conductivity, for example, management zones and site-specific management and variable rate applications, and map principle. So in this session, we are going to talk a little more about the maps, and especially we are going to talk about the yield monitors and the NDVI and how we can use those informations. So for review, we talked about precision agriculture is all about management using technologies. And with these technologies, we can address the variability in a field, which we discussed. We have lots of variability in a field. So if you look at the precision agriculture, it's very complicated. But if you come closer, it's all about management. Management is the key. So you will collect lots of information related to, let's say, soil. And then based on the soil data for first step, you're starting, you'll write prescription map based on the soil data and the weather and the crop. So later, when you see the crop after emergence and after you have good stand, again, you will collect lots of information related to crop health. And based on that, maybe you can apply side dress and improve the healthiness of the plant in term of fertilization or plant protection. And finally, when you're done, you will have yield monitor to read the yield data and collect information about the yield per unit area. And again, this cycle, next year, you will use this yield data plus, you will make yield maps plus soil data again and again, and you will have this cycle year over year, and you will refine your data or your decision based on more information and facts you will get from your field. So we discussed the primary precision ag steps management zones are to find and identify the soil variations, to create different zones and treat each zone separately or individually. We also talk about the grid sampling versus soil management sampling, management zone sampling. And we mentioned with grid sampling, we will have more number of the soil samples with grid sampling. We are not informed. It's kind of I'll thinking about blind sampling because we are locked into the grid and we don't know which part of that grid is with what type of soil do we have there. Also, we discussed about the writing prescription map and on-farm research because I mentioned when we work with farmers, we don't want to bother them. We want to help them. So in order to not bother them, we have to just follow and be matched with their schedule and be, we don't need to change what they are doing. We have to change and accommodate with them. Means whatever they are doing, we have to be follower and follow them. So for that reason, if you look here, in auto steering mechanism or controller for tractors, we draw AB line, and farmers for each field they use the auto steering system, they draw AB line for maybe each operation. And for example, for planting, they have one AB line. And if I want to do the on-farm research, I'll take that AB line and calculate the width of the tractor and shift that AB line half of the width. Let's say you have 40 feet of the width of the planter. I will shift the AB line 20 feet. It doesn't matter right or left. So, and repeat that one and make a net of the means parallel lines. So, can you unmute yourself and tell me what are those lines? AB lines is the center line of the tractor and the auto steering guiding system. What are those new lines which I draw? Do you have any idea?
Is that the edge of the planter then?
Sorry?
Is that the edge of the planter?
Yes, very good. So what do we want to get from here? When we have the edge of the planter, we will put our plots exactly on those secure lines. We don't, overlap from, one piece to another or one pass to another pass. So with doing this, we don't bother farmers. All we need to do is changing the rate on prescription map, and we'll give it to farmers. Go and plant your field based on this prescription map we discussed, for example. Does that make sense?
Yep.
So now we discuss about this. We have different zones, let's say 3, 4, maximum 4 or 5, not more than 5, even for on-farm research. So when we have different zones, for each zone, we don't want to do research. We are talking about the on-farm research. On-farm is before the research, means we for sure we don't want to reduce the yield for farmers. Again, I repeat this one. We are there or as extension to help. We are not doing research only. Of course, we are going to do some research just for farmers, just to show farmers how you can improve your yield. So for that reason, in some area with high potential yield, for example, here, we don't apply lower seeding rate. We don't have 28,000 here because we know in high potential area, we don't need to apply less. Means at least we should get to the flat rate farmers doing, or maybe more. We want to say to farmers, cut seed from some part of your field and put it some other part. Just do, we calculated flat rate. For example, you are putting 36,000. We calculated it would be N number. We will plant this N number into your field, but we will cut it from some area and we'll put it some other area. And it does make sense. So just like we don't plant low seeding rate in high potential area, we don't plant high rate in low potential area. And for ages, we will go with, or header, we will go with 28, 20, 30. Here, just for corn, I'm saying. And I think we had this slide. The result is very promising. It's proven to be, applicable. And I think I read this code, and the farmer is going to continue that. But to emphasize that, we applied 28,000 because of the soil type and the information farmer had or grower had for his field. 28,000, but yield was close to 190 bushels per acre. So we planted 28,000, we got 190. But here we planted 40,000 and we got just like that, means 190. So what's the reason here? Are we missing something? What's the problem? And the reason we planted 28,000 here was because of the historical yield and the information the grower had. So now there is a question here. Why with planting 28,000, we got 190, but same time we planted 40,000, we got almost the same yield. What is this? And one answer I'm thinking would be the competition. So if you plant 40,000, the competition would be higher and the yield would be, lower. But the same thing here happened. With, let's say, 32,000, we got more than 190 bushel per acre. And so the point is, we can cut from some area and plant it some other area. With year-over-year data and information, we will realize that 36,000 flat rate would be the limitation, the top roof of the, seeding rate. We don't need to cross that line. So if we don't cross that line and we cut from some area, means we are saving on seed upfront. Means we had flat rate 36,000, but now we are cutting it for some area, and still the yield increased. So very good. Next topic I want to start is stand uniformity. So when we have variability in soil properties, we will have non-uniform stand, back and forth emergency, and when we have non-uniform stand, we will have non-uniformity of maturity, and when we have non-uniform or ununiformity in maturity or non-uniformity in maturity, we will have problem for harvest, and the quality may decrease because of back and forth. We don't know if we go and harvest now or wait for more maturity, if we are going to lose some seeds, or there would be problem. So the stand uniformity depends on seed, soil, water, and bed preparation, fertilizer, and especially for the emergency would be soil temperature. The soil temperature is, I would say, the important factor for the uniformity, stand uniformity. But for maturity, uniformity of maturity, the stand uniformity itself plus plant population and nutrient management would be the factor. So if we have higher population, the maturity we will have delay in maturity usually. Or on nutrient management, if we apply more percentage of nitrogen for some area, or we have excessive amount, let's say we have, based on this the variation in soil, we have some fertilizer or nutrient in soil, and now we are applying flat rate fertilizer. We are applying flat, but because of the soil properties, it means we are applying, or we have some area, and based on that, we will, change the uniformity of maturity. So, as I mentioned, the temperature is an important factor. Just by having a slope, I'm not talking about the hill or mountains. Just you have seen this one, very mild slope. When you have south face slope, it will get more energy from or light from sun, and in the spring you don't have snow on south face slope, whereas for north face slope it would be cooler, and it's just because of this simple phenomena here. We will have intense energy or light per area. So the same, let's say the same band of the light would cover only this length or this area, but the same amount of the energy or light would cover this area. It's just almost, double area means half of the intensity. So this is one big factor here. Another factor, soil type. Soil surface temperature for bare soil. This is an article, is fact. And the maximum temperature measured was 55. These are same time, so it means it's comparable. It's comparing apple with apple. We don't have a doubt to say, oh, when did they measure this? No, it was, scientific measurement. That's why they could publish. It's pre-reviewed journal. So 55 for sandy soil and minimum 41 for clay soil. 14-degree fluctuation. And just think about this. For some seeds, when you have lower temperature, even your seed would not activate it to get prime and emergent. So if we have different soil type in our field, and we treated, when I'm talking about the treatment, I'm talking about the planting depth, I'm talking about the fertilizer application, I'm talking about the seeds. If you treat your field all same with flat rate of inputs, think about it, some area you'll be a lot behind and you don't have, and some other area it would be very fast and advanced, and definitely you will have non-uniformity in maturity, and you will have problem. So now, if you have cover crop for same soil, think about it, for both or for all soil type, the max temperature and mean temperature are lower, and fluctuation is lower. The temperature differences is lower. So high temperature is for sandy soil is obvious because absorb more heat, and low for clay because it's more moist or with higher moisture content, and the fluctuation is 7 degrees. It means Of course, with cover crop, you are pushing your window, means you cannot plant, or even if you plant earlier, you will not get anywhere because of the soil temperature. You don't have that activation temperature for seeds. But the point is, you have minimum soil temperature differences, so you will have better uniformity. Here, if we go subsoil temperature at 4-inch depth, so now look, it would be cooler. Now here we don't have cover crop, but the fluctuation, same measurement was 14, but here we have 10-degree fluctuation. And if we have cover crop and we go to measurement on 4-inch depth, we will get only 3-degree differences. So with all of this, if we put it all in one picture, we think if we have this condition, for example, with cover crop and adjust the depth, we can manage the optimum temperature to have uniform stand or better uniformity. So soil temperature, with the takeaway from the charts and what we discussed was soil with cover crop would be cooler, the soil, higher organic matter, darker the soil, warmer the soil, higher soil moisture content, cooler the soil, deeper in soil profile, cooler the soil, but less temperature fluctuation. So we have all of this information, and with this information, if we want to minimal impact on uniformity stand, we can have variable rate application of cover crop, or we can change. Let's go back to this slide. If we plant with higher canopy cover crop on south-facing slope, and with low canopy like tillage radish or some smaller leafy plants or cover crop for north face, and with woody stuff for south face, we will adjust the temperature. Here we will have more cover crop, and it would not let the moisture to evaporate it. And for that reason, here we will have cooler because of the canopy and the shade of the cover crop canopy. And here of course we had cover crop, but we don't have that big bushy and canopy, so we will get higher temperature or closer to the south face. So as I mentioned, we can design a variable seeding rate for cover crop to compensate the variation in soil temperature. And on other word, I'm cover crop for a field to address the field variation. Something here, we have one system. This is up-to-date system, which we have two type of downforce for planter. One is hydraulic downforce, and another is pneumatic downforce. The pneumatic downforce is older version, and the time response for the pneumatic downforce was close to 20 seconds. But by that time you already passed the obstacles or what or a rock or whatever caused you need a downforce, but with 20-second time response, you already passed the obstacles or that problem or that issue, and you cannot maintain the uniform depth. So they designed the hydraulic downforce, much faster response, as I mentioned, 1 to 20, 1 second for hydraulic and 20 seconds for pneumatic or pneumatic. So I have a video here. I'm going to play it. It will explain the two mechanisms. Can you hear this?
Work in harmony. Together they provide the most sophisticated seating depth control system ever developed.
Yes.
We use individual hydraulic cylinders to push the openings down, because these maintain the same downforce throughout their entire stroke length. Then we mounted the openers and coated linkages so that all angles remain constant. Then we gave the openers a pair of adjustable crucibles for positive location on the cell surface. Surface ups and downs, and so openers are conveyors on top side, containers of the surface surface. Phillips moving that up, right tools doesn't. So that makes something good control for right tools.
This is another system.
50 to 450 pounds of line downforce. Provides an accumulated the system is well controlled since started display. Oils to keep a consistent amount of oil in the margin of the changes. So it's typical of the engine to the wire properly downforce. So for instance, if you're having some failure in your wheel tires, the system will apply more downforce that will provide your optimum seat trench to make sure you maintain depth and keep your ground contact at 97%.
So based on these two clip or these two machines, they maintain uniform planting depth. But this is not what just I said. This is not what we want. We want some area to plant deeper or some area to plant shallower to compensate this temperature or the variation which cause the non-uniformity. So for that reason, we were talking about the variable downforce pressure. But the newer system, which no one has designed it yet, is variable planting depth. And we will design a machine to change the depth based on the needs to address the soil variation compensate the aspect impacts and address the soil thermal variations. So let's switch the gear and talk about the NDVI. Now this is introduction to NDVI. It's normalized difference vegetation index and indicate or is an indicator for plant health and vigor. So basically, leaves or plants, because they have chlorophyll, observe the RGB light and reflect the near infrared. And if you look at this picture, the amount of the green reflection is more than the blue and red. For that reason, we see the plants are all green. Why don't we see them as a near infrared? Because that's not visible for us. We cannot see it. Does that make sense?
Yes.
So, in other words, if the plant is healthy, it would reflect more green. And we will look at that plant and we'll see, oh yeah, this is very healthy and green and darker green. But if it has some stress or problem, it will show other color. Just like, fall, we will see the stress. Okay. So how the NDVI calculated is near infrared minus red divided by near infrared plus red. Look, this is healthy plant and this is a stress plant. I don't want to say unhealthy because in fall, the plants are not unhealthy, they just fall. So you can see the reflectance of the near infrared would be almost same, means not really changed, but the reflectance on visible red or blue is different here. If you compare the healthy and a stress plant. So for healthy plant, you will get higher number of NDVI compared to a stressed one. And this is a simple way to look at the NDVI. So how can we use NDVI? We will collect information. We fly over with drone. We collect information with near infrared. And we have another camera, RGB, means normal camera. And we will take these two picture. Now we have some sensors or cameras at the same time with one sensor. It would calculate all, take different band and put it together and calculate it, and it will give us just NDVI. Sometimes if we have separated image like near infrared and RGB, we can calculate it and we can have different algorithm or the equation to adjust the NDVI based on what we want. But when you have NDVI camera, it sets a program or equation just like that. Remember, we were talking about the near infrared minus red. If we want to calculate it very precisely, I will go and calculate only this spectrum for near infrared and only this area for red. So for that reason, I'm saying if we have different cameras or different images, we can calculate it. If we don't, it would calculate it, means NDVI camera would calculate it for us. So we'll take these two images to a QGIS, which is open source software, and we'll put it together. And based on the calculation, NDVI calculation, we will write prescription map. That is, cutting edge, at least for now. So if you remember, we were talking about the temperature, soil temperature. If we have thermal camera on drone, at the same time we will get the soil temperature, and we can make a decision or manage the soil temperature and adjust the soil, the depth, planting depth, or fertilizer application. Maybe we can compensate that. Maybe if we collect thermal imagery, it will show us some area with lower temperature, you will have higher moisture content. Or some area with with higher temperature, you will have maybe higher organic matter. It will reveal some information if you can interpret it. So this is a corn leaf taken by near infrared. Just I wanted to show you, this is real green leaf, but when you take image with near infrared, it looks like that. This is also the picture taken by near infrared camera. So if you want to have some idea about near infrared, the minimum about NDVI, the minimum number for NDVI is clouds, snow, and the maximum is, for dark or dark green, plants, and which covers all the ground. That would give you the highest number. We mentioned here 0.6 to 0.8 for the highest number, but that could be up to close to 1. We don't have exactly 1 because when we have when we take image from optimum height, we will have lots of reflections from, because we have lots of angles of the leaves. We don't have we don't collect all the reflections to the camera. For that reason, we will have always less than 1. So if in the other word, it would start from 0 to 1. And here we have minus because just for snow, it would observe all near infrared, and basically it doesn't mean anything. So for plants, it would start from 0 to 1. How this NDVI would help us? We discussed, I think with Dale, we discussed the enriched strip. When we have measurement of the NDVI for a field in different zone, we will get different numbers. And based on those different numbers, we can decide how much side dress, how much fertilizer we want to apply. And we have one program called nitrogen rich strip. How it works, okay. We apply nitrogen to, for each zone, we have a band of nitrogen. We apply it in a way that plant cannot take it. Means we apply more than enough. Think about it. If we usually apply 120 to 100 to 200 pounds of nitrogen for a particular zone, zone number 1. Now we are going to apply more than 200, means close to 300, and we are sure this zone or this plant in this zone cannot take that much. Means you are thinking it can only take maybe 250, 260 maximum in best condition if you have. But so you will, when you are sure the maximum is 260, you'll go and cross that line, 280, for example, pounds of nitrogen. And you will have reading from the enriched area, the area you applied high amount of nitrogen. And you compare it, you measure from the enriched area, you compare it with field. And this comparison would show you or would tell you if you had applied or you apply the high number of nitrogen, like 280 for your whole field, you will get to this NDVI. Now you will calculate this one, and you will see if you have 0.88 in your field, which is equal to your enriched area. Now you tell me, how much nitrogen should we apply? Look, we have enriched, we applied 280 pounds of nitrogen. It reads 0.88 NDVI. We measure the field, it reads the same number, 0.88. It tells you, even if you apply 280 pounds of nitrogen, you will get the same thing. Means you don't need to apply nitrogen. You don't need to apply anything here. Just by not applying any fertilizer here, you are good, because with no application, you are same. Does that make sense?
Yes.
So if you have, thank you there, if you have higher differences, means higher gap here, that area you need to apply more nitrogen or citrus. So what do you need to do that? You need one important thing, planting date, NDVI from enriched area, NDVI from field, and maximum. These are the equation. So we have one app. You have to put these information. But even if you don't have a maximum yield history, still you can manage and you can decide how much nitrogen you have to apply. And also you need to mention if this is irrigated area or dry land. So it's obvious that nitrogen is very important, and in a reduction of 20% would save growers 1.2 billion annually. And so because it's very important, we work on this project. We had applied different range of nitrogen, and we measured NDVI from the field and enriched strip and compare it with all of these plots, and we developed algorithm for that. This project is done in Clemson, and as I mentioned, this is very old. It has very long history, and the background is I think it started maybe 40 years ago. I don't know. I'm not sure about exact year, but at that time they didn't have the green seeker. They couldn't measure the NDVI. Just by looking at the plan, they had ramp application, and they could decide, okay, at this area, it's matched with our field, and when we move on ramp, it would get darker, but after some area we don't have any changes in darkness of the plant, and all these observation done by man means they just look at the plant and decide about the number or colors. Now we measure it easily with NDVI, with GreenSeeker. So if I want to explain it a little more, the in-season, when we have the NDVI measurement, remember I said about the day after planting, if we want to predict or estimate the yield, all we need to do is, based on that algorithm, NDVI divided by days from planting of sensing. And so we have to place the enrich, as I mentioned, establishing the nitrogen-rich strip, which would be number of rows, more nitrogen than the plant can take or use it. And now, I mentioned we measure the enrich and we measure from field. That's response index. And if the response index is 1, it means we need to apply 0 nitrogen. Is that right? Is that right? If we get means equal number from enrich and the field, it means we even if we apply that excessive amount of the nitrogen, you will get the point I am now, means just same number. You will not increase it. Right. So if is that make sense?
You're saying if the NDVI numbers are relatively same?
Yes. So if the response index is 1, means when do we have the response index equal to 1? When we have the NDVI from the nitrogen richest is equal to nitrogen from field. So when these two are equal, the time response would be equal to 1.
Yep.
So yes. So when we have this time response is 1, it means we don't need to apply. Means the soil on that area has enough nitrogen. You don't need to apply anything. But when the number from the enriched strip, the gap between these two numbers from field and enriched strip is bigger, it means you can apply more nitrogen. But how much more? We'll get there. Oh. So this is what I explained it, right? Just now. Remember, I mentioned we have yield potential. We can estimate it with NDVI. So we have yield potential with the NDVI, in-season estimating yield. And if when we apply or when we establish the enriched strip, we will have, without applying nitrogen, we have in-season estimation. But now we have enriched strip. We will mention this one. if we apply that much nitrogen, the yield curve, instead of being here, would shift to higher level. So here with no nitrogen, just estimation of the field and the days after planting. Here is when you apply nitrogen on enriched strip. On those area, you will see obviously most of the area you have higher NDVI. So it would shift the yield curve to higher level. But so how high? It cannot go to the sky. So we have one yield potential, the maximum. You cannot harvest 500 bushel of corn per acre because of the limitation of the weather condition or water or soil. Not more than 600. Definitely. So you have the yield potential max here would stop you. And now we are going to calculate the because the nitrogen are not pure nitrogen, so we are going to calculate the percentage of the nitrogen and the percentage of the uptake from the plant. And as I mentioned, when your NDVI would not change, means for in season is high enough, you don't need to apply, it will go down the amount of nitrogen you need to apply for those area which you estimated already you have higher yield. So this estimation is corresponding to the area you don't need to apply nitrogen. So this is little complicated, but if you need, I can explain it little more in depth and do some clarification for these curves. So do you have any question here? Okay, so
Nope.
thanks. We'll move to next. So we compare these, farmer's method, means conventional, and the NDVI measurement, as I mentioned, that was at Clemson, and we saved 21 and 34% of the nitrogen. And we have differences here is because of the difference in zones. So this 34% is belong to area with lighter soil but higher potential, like sandy loam. So sandy loam, at the beginning, it would show you lower NDVI, and you are thinking, okay, you can apply more nitrogen. But later, it would show you the potential. So we have for two zones, both beat the farmers and save nitrogen. And for yield, we didn't have any yield reduction. Even we apply less nitrogen. Sometimes this was not significant. I don't name it. We beat the farmers' practice because the numbers were not significant. Was higher, but not significant. So now we done the nutrient management, we get to harvest. We talk about the yield data and yield maps. And now we are going to talk about the yield monitor system. So we have we have a computer to, use the GPS, moisture sensor, and mass flow sensor data, and put it as a, one signal, tagging with location, and store it as information related to the particular area. So the sensor we use could be mass flow sensor or volumetric flow sensing, which for mass flow sensor we have impact sensor, we have a load cell, and as the material moves, hit that impact plate or sensor, and based on that you'll get pulse how much material are moving. And radiation is when you have one radiation maker and one detector, and how when the material moving and crossing this radiation beam, based on the cutting the radiation, you will get information about the mass or mass per time. And for volumetric flow sensing, we have photoelectric sensor, which we have a sensor to look at the material moving, and it would get some detect the reflectance of the material, and based on that it would calculate how much material are moving. And the old version was paddle wheel, which all the material would go to the paddle wheel, and based on the rotational speed would the material cause the paddle wheel start rotating. You'll get pulsation per RPM per second, and you will get idea how much material you harvesting per time again. So how it works? So we have width of the combine or any harvester. I don't want to mention just combine. And you have GPS, and you are moving from point A to point B. So you have length and the width. And with these two parameters, you can calculate the area. So with this area, now you calculated the mass. So you have yield per this area, means you can calculate it in real time. Based on the frequency of our reading, you don't need to move this long distance to get the yield data or number. Based on the frequency, sometimes we can adjust it to collect, let's say, with interval of, let's say, frequency of 100 readings per second, but it would make average of every 2 seconds, and send the signal that was the number for these 2 seconds. We can adjust that to make it accurate, or sometimes you'll get a wrong number if you just go fast and slow it down, and because of that you will need to adjust it, and that's average, making average of the numbers would help to adjust it and make it more reliable. So I have a question here is related. The answer is not just with the yield monitor, or maybe yes, little related to that, but I have a question here. If we are thinking per, as I explained how we collect the yield data, do you think if this color area is the yield data, is it correct? And for example, here is lower yield, here is higher yield, and it can be correct or something is wrong with this map?
Isn't it just kind of averaging it for that area?
No, it's not averaging that. But my question is, can we have one number for here, this point? Can you see my cursor?
Yep.
And can we at same time on the width of the harvester, we have one number for here, one number for here, and another number for here? Is it possible?
I don't think it's possible for the yield monitor because the head just is going to average across the whole head for the yield monitor, isn't it?
Very good. Yes. So these pictures, some of these pictures are for advertising of the precision ag, and one of my friends gave me this picture and said, "Oh, look, I designed this one." And said, "What is this for?" Said, "For yield data. I want to show you." Come on, how can you explain this one? The color should be just parallel to the head. Otherwise, how could you get number here? And of course, he corrected and said, "I'm going to use this one for for my presentation." So anyway, so we discussed about the different sensors, and we don't discuss it anymore because it's just mechanical, and we cannot use this type of information. Just for your information, we have paddle wheel, we have impact sensors with different type, and we have radiation mass flow, one source of radiation, and a detector or receiver. And one important thing here is moisture sensor. Think about it. We harvest 200 bushel per acre, means the yield monitor is showing 200 bushel per acre at 20% of moisture content. And another field, we harvesting 160 bushel per acre, but 15 percentage of moisture content. Which one is higher, and how we can adjust this? So we need moisture sensors. These are almost two same numbers. But when you have that moisture sensor, it would calculate it and it would compensate it based on the marketable, moisture content. And even if you have 220%, it would calculate it and make it with 15%. That would be very easy for the calculation. So as we have discussed, the main purpose of yield monitors are allow the manager to precisely monitor the yield and use these yield data to make yield maps. And when we have yield data, we can identify which area we have higher yield, and we can find some problems area. We can find, based on that, we can write prescription map. And over years, we can compare it and classify it with the yield wet or dry year. And when you have the dry year and yield for both year, when you have for wet and dry year yield data, you can compare them and you will find out some area of your field, no matter what, you have wet year or dry year, you have good yield. Those area always you can have higher seeding rate, that would be high potential area. And some area, always no matter what, you have low yield, always you can consider them as low potential area. Something in between, which I would say the majority of our field would sit on that between, means not really good, not really bad. And in between, some area on wet year, you will have higher yield, but the other area you have on dry year higher yield. So based on these information, you can realize some problem with drainage without even going and sample your soil. On those area which you have lower yield in wet year and higher yield in dry year, you can say you have drainage problem. Or the soil type, when you have heavy soil, which when you have wet year, the yield would be down, but when it's dry year, would be better than area because it would hold more water. The vice versa. If you have some area on dry year, you don't have good yield, but on wet year, you have good yield. It means the soil is lighter, but you have potential. So for both soil type, means this problem which I explained, if you add organic matter for those area, you can improve your yield. And for those area you have drainage problem, you can find out and do the management. Maybe you need to just do subsoiling. Then you can, when you find your problem, you can find the solution. So one important topic is calibration. So what do we need to calibrate a yield monitor or a yield monitor system? First of all, we need to calibrate the moisture sensor. How to do that? There are different moisture sensors. There are instruction to read the moisture and to measure if you have a real thermometer, which should not be in light or in directed by or impacted by temperature from equipment. When you have real temperature with your measuring with your thermometer, you will go and read on your monitor what's the temperature reading from your temperature thermometer on your yield monitor. And also for moisture sensor, when you harvest, you are reading moisture from the harvested grain, and you will take a sample from the harvested grain and get exact moisture percentage, and then you can come back to your yield monitor and adjust that one based on the if you are off of the readings. So the first step is adjust the temperature, the moisture offset, and now we have to harvest a known area, which, so we know the width of the head or the harvesting machine or the platform. We know the width of the machine, and we harvest a known length. Multiply by that width would give you the area, and you need to weigh the harvested material, whatever you are harvesting, grain or sugar beet or whatever you are harvesting, and calculate the yield. And if you are off, you have to find out why are you off and what's the problem. And for that, you need to repeat this calibration method. So when you harvest your yield and you with really good scale, you have to think about the marketable moisture content. As I mentioned earlier, when you have 20% moisture content, you cannot say, oh, okay, really good. I have 200 bushel per acre now. No, you have only 160 because the marketable yield would be at rate of 15% moisture content. And so when you calculate all of this and you will find out everything is working correctly, you have to repeat this one. They mentioned you have to repeat this one or recommend it 3 times. If you were offset, you have to, after fix everything, any moisture offset or temperature offset, whatever you have, what problem you have, again you have to go back and repeat it two more times and to make sure it's working correctly. And for sure, if we want to collect or use this information, we need to have correct data or right data. So this is related to the, I'm going to change the topic. When we harvest, we will take the material to a storage and bin, and we have to do the aeration and dry them, and we have to reduce the moisture to lower level, compared to the harvest time, to be able to store them for longer time, and then when times come, you can sell them. So if you don't do that, maybe you will have lots of loss due to the storage problem. So we have this topic, equilibrium moisture content. It defines as when there is no exchange of water, any form means any form, between material and surrounding. And effect of air temperature changes equilibrium moisture content. Increasing temperature at the same humidity, relative humidity, increase the capacity to absorb moisture. Increase the air temperature at the same relative humidity, increase the capacity. I mentioned increasing the temperature at the same relative humidity, decrease the equilibrium. Means if your air temperature is higher, but relative humidity is same, the equilibrium moisture content value would decrease. But if you increase the air temperature at the same relative humidity, the capacity to absorb moisture would increase. So increasing the air relative humidity at the same air temperature increase the equilibrium moisture content. So what does that mean? If you have higher relative humidity, but you are changing the air temperature, it would change the equilibrium moisture content. So I have one chart here. With increasing the temperature, and with same relative humidity, you can see, for example, 60% here. By just increasing the temperature, the equilibrium moisture content would change. For example, here at relative humidity of 90%, and the temperature of 65 degree, you will have the equilibrium moisture content would be 20.1. But same, if you increase the temperature, the equilibrium moisture content would reduce. Why do we need this? Why do we study this? I want to mention this one. If you have this chart and when you harvested your material, oh, you don't see the chart yet.
No, we don't. There we go. Well, there it is. Thank you.
Oh, I'm sorry. I'm
All right.
Yeah. Okay. When you have same relative humidity and same relative humidity with known temperature, the equilibrium moisture content would be a number. On same relative humidity, when you increase the temperature, you are decreasing the equilibrium moisture content. So now, what I want to get from here, if you do the aeration, you harvested your material, you transport it to bin, to a storage, and you start aeration, you are at 20.1% of moisture content. And when you started the aeration, it was 90% relative humidity, and the temperature was 55, so you were 21.4, and you continue, the temperature moved, and you did aeration, and you are in 20.1. Now, think about this. Tomorrow morning, if the temperature is 40, and even relative humidity is 85, means less, and your aeration system is working, you are adding, I was talking about 40. You are adding moisture to your storage. It means you should look at these numbers to not let your aeration system or drying system working all the time when it's not needed. Hope it does make sense. It's a little complicated. So we have one system. Again, this is not a new system, but the remote sensing is new. We have put the moisture sensors here and measuring on real-time relative humidity. And based on the previous chart, based on this chart, which I explained, it would shut the system to not add water to the storage. So with these, sensors, you can get idea what's going on in your bin, and you can manage your bin, your material better, reduce the entry to the bin, which is very dangerous, and always you can have idea, and you can reduce the risk of the loss due to the storage problems. At Clemson, we did this monitoring system, and with using this system, we reduce close to 80% of energy usage just by running the system on the time which would be the optimum time, and shut it when we don't have that optimum relative humidity or temperature. This is very good system, I would say, which I didn't see it here at upstate New York, and maybe in future that would be part of the storage if you want to reduce the the energy usage. And when you reduce, let's say you harvest your material 20 to 21% and load it there, and store it, dry it to 13%, or for the percentage you want to store it. Later, when you want to sell it, you can rehydrate it to marketable number or moisture content and sell it. Finally, again, I'll repeat this one from the previous slide or previous sessions. We collected lots of information. We need to organize this information, and later, first of all, we need to calibrate it, validate any type of information we are collecting. And then based on those information we already have, we do farm planning, and we analyze it and archive it for next year, and we refine it when the next information come in. And so if we have years of historical information, we'll be better off. We can have informed decisions. Again, I have this chart, the same thing. We cover almost all of these parts, and if you have any question, I'll be available. Now we have time maybe, or later you can email me or call me, and we can discuss any information if you have.